These are the notes about isotopes and atomic mass. So as a reminder, the difference between atomic number and atomic mass is that atomic number is just the number of protons. So if we look at this nucleus down here, we can see 1, 2, 3, 4, 5 protons. And then the mass number is protons and neutrons. So then we would count all the particles in here, which would be 5, 6, 7, 8, 9, 10, 11 total particles. Elements can have different numbers of neutrons, and the neutrons inside of the nucleus affect the mass of the overall element, the overall atom. Each different version of an element is called an isotope. So carbon 11, carbon 12, carbon 13, and 14 are all different isotopes of carbon. They all are carbon, but they have different sized nuclei. You can think of isotopes as bowling balls because they can come in different weights, but they're all still bowling balls. Just like these isotopes come in different weights, but they're all carbon atoms. So here is a carbon 11 atom, and a carbon 11 atom has a mass number of 11. That's what that 11 stands for. And if we look over here, there are 11 total particles in the inside of the nucleus. There are 6 protons, which are the red dots, and 5 orange ones. Now, carbon 12 is a little bit bigger for a mass number, but you'll notice that the protons are still 6. So the only difference between carbon 11 and 12 is that now there's another neutron. And we'll see the same thing happen if you watch over here. When we go to carbon 13, this is the only new particle, which is another neutron. And so the mass number continues to grow because we are adding more neutrons, making this carbon atom heavier, but we're not changing it to a different element because it still has 6 protons, and any element that has 6 protons is carbon. And the last example here, the last isotope, has a mass number of 14, and if we look, there are 14 total particles in the nucleus, but 6 of them are still protons and 8 are now neutrons. So if we compare all of these carbon isotopes, we'll notice that the number of protons is the same for all of them, but the number of neutrons changes, and that as we get more and more neutrons, then the mass number of carbon also increases for each isotope. We are going to use a different notation in this homework, and that is the element symbol with the mass number and the atomic number next to it. And these will both be whole numbers because this signifies one specific isotope of an element, whereas on our periodic table, the mass number there is actually a weighted average that we'll talk about later in these notes. So for example, down here, we've got O as the symbol, and if we look on the periodic table, that element is oxygen, and then the atomic number is the lower number. So for a number of protons, it is 8. And then for number of neutrons, we have to take the mass number minus the atomic number. So we're taking 17 minus 8, and that gets us 9 neutrons. So that the total number of protons and neutrons is equal to that mass number on the top left of our atomic notation. What would happen if you change the number of neutrons in the atom? That's basically what we did to the carbon isotopes. So if we have this isotope of oxygen 17 and we add 1 neutron, what will happen is it will get heavier. It will become oxygen 18. But it stays oxygen and it stays with 8 protons because we just added a neutron to the nucleus, making it fatter, but not making it a different element. So the results are the mass changes, the element stays the same, and it's now a new isotope. For protons, what would happen if we change the number of protons in an atom? If we were to add 1 proton to this oxygen isotope, it would change lots of things. So first we see that the atomic number increases because that is the number of protons. We also see that the mass number changes because a proton is a subatomic particle in the nucleus, and so the mass of the atom also goes up. And then the symbol also changes because now we no longer have oxygen. Oxygen has 8 protons, and this new element has 9 protons, so we've actually changed it into fluorine. So the mass changes and the element changes. Really, every part of our atomic notation changes. Here's some practice. If you want to pause the video and try to write these down and consider how many particles each of these isotopes has, you can do that. So boron 11 has 5 protons given by this number, and then 11 is the mass number, so we subtract to find neutrons of 6, and then the electrons and the protons are still going to match on this homework. For sulfur, we've got 16 for the protons, 34 minus 16 for 18 neutrons, and then the electrons and protons match. Some isotopes are more common than others in nature, and so the average atomic mass listed on the periodic table is a weighted average for all of the isotopes of that element. When we are calculating this weighted average, it's really important to convert percentages to decimals so that our numbers are the right size. And so to find an average atomic mass, you take the percent abundance of the first isotope times the mass of the first isotope, and then you add that to the percent of the second isotope plus the mass of the second isotope. And if there's more than 2, you continue this process. These masses are going to be whole numbers because they're just the number of protons and neutrons. So for example, with the carbon before, this would be 11 and 12 and 13 and 14, whereas these would be the percentages of each one of those isotopes and how often they're found in nature. So if we looked at 100 chlorine atoms and 76 of them were 35 chlorine, meaning that they had a mass number of 35, while 24 of them were 37 chlorine, find the average atomic mass. So what we need to do first is calculate the abundance. So because there were 76 out of 100 atoms of this first isotope, the percent abundance of that is 76%. And then 24 out of 100 would be 24%. And then to calculate the atomic mass, the average atomic mass, we're going to take the decimal form of this abundance times the mass number. And then we're going to add it to the percent abundance of the second isotope times the mass of the second isotope. And when we do this, we get 35.48.